Assalamu alaikum. I am Asad Yusuf. Welcome to MPT channel. Today's topic is monetary unit and absorbed dose calculation. So objective of this presentation is to understand the basic concept of dosimetry, recognize the fundamental quantities like TMR, TPR, scatter factors, percentage, depth doses, able to apply these concepts in application and calculation. Dose ratio and monetary unit calculation. So for the dose ratio, think about the measurement made in a water fountain. Define the quantities, the ratio of doses at 2 points, 1 point different than other because of the distance, depth, and the condition. Whereas a mu calculation use those ratios for the clinical calculation. So distance, how far away from the source, depth, how deep in the absorber, and different than the distance, scatter contribution from the surrounding to the point of interest. So these are the parameters which we usually use in our calculations. PDD, TAR is an old parameter, but still has some application. TPR. Dose ratio parameter for calculation include equivalent field size, minor factor, relationship between PDD and TMR has to be understood, scatter factors, wedge factors, stray factors, off-axis ratios. So what does mu calc mean? How to set the mu monitor, mu meter on LINAC to deliver a certain dose at a certain point in the patient for certain beam energy, field size, collimator opening block field, depth, distance from the source, modifier. So what is the dose in centigrade for certain mu setting? That's the question. Where did the monitor come from in MUs? The word comes from pancake-shaped ion chamber called monitor chamber in the head of LINAC. What does the monitor chamber really measure? Monitor ion chamber signal is proportional to the number of photons crossing it before the beam is collimated. Regardless of how it is used below, we need to know how much produced in order to deliver a certain dose. Why not use a beam on time? If the machine could produce a photon at constant rate, we could use centigrade per minute, but the machine fluctuates. Also, the dose rate can be set to many different values. In Cobalt 60, the output rate is very constant, so the dose rate measured in centigrade per minute. In LINAC, dose rate is measured in centigrade per mu. So standard calibration method, we can't measure photons simply a fluent. So we need a reproducible reference calibration setup. It is calibrated by a physicist as per required to ensure accuracy of absolute dose to the patient. Usually it is 1 centigrade for each mu delivered at some reference depth and field size distance. So these are the standard setup. One could set as a SAD calibration or SSD calibration. The difference is source to axis distance and the source to surface distance of 100. So these are some other setups. And if you incorporate, if you vary from the standard distance, then we need to calculate the output factor for that. And also if you add a modifier, then the output factor will be different. So those vector need for deviation. So this is what we required, and due to the difference in the depth, TMR will account. SAD change, the inverse square law could be used. SAD change, then the PDD could be used. And the modifier is added to these wedge factors, transmission factors, tray factors are incorporated. The basics of photon is inverse square law. The photon coming from the point moving in a different direction has to spread out. So the distance at R, intensity at R distance will be different from a 2R distance, and it will be 1/4 of the initial one. In such a way, it will decrease, and then that's the formula one could follow. If the photon from a point source are incident on water, there is a decrease in intensity due to divergence, inverse square law, decrease in intensity with depth due to the attenuation caused by the photon interaction. Scatter also produced in a photon interaction. The dose factor account for the changes in attenuation, inverse square law, and scatter due to the changes in the depth, distance, and field size. Dose closely follow the electron released by the photon, which is closely follow the photon intensity fluence. This is an example, and listeners can try themselves. So PDD and TMR ratio. Here you can see the source to axis distance is same and the SSD is varying. The dose at depth, the dose is the Dmax. This is called TMR. Whereas here the SSD remains same, the depth is difference. The dose at depth and dose at Dmax. This is what the PDD is. So the TMR contain attenuation and scatter changes with increasing depth at constant distance from the source. So it is independent of SSD. PDD contain attenuation and scatter and inverse square law changes, so it's dependent on SSD. And this is the variation between these two data. So that's the question. Juggle up your mind. So the 10 photon field, the TMR and PDD are both one output vector at the depth of Dmax. At depth 10 cm, the TMR is larger than the PDD. So this is because of, so this is what you have seen, the TMR is large as compared to PDD. So PDD contain inverse square component, that's why it is low. So another question, TMR for 10 by 10 4 MV photon field at 100 cm SAD is 0.73 at 10 cm depth. If the SSD were changed from 90 to 95, the change in TMR would be. So if you go to the picture again, here you can see. So the depth changed. Oh, sorry, the SSD changed, but the depth remained the same. So the TMR will remain the same. So there will be no difference. So TMR will be 0. 0 will be the answer. So output factor. When you change the field size, the calorimeter scatter, the head scatter, and phantom scatter varies. So generally, a slow variation in the field size and many problems involving change in field size can be neglected. This is how the factor is incorporated. So this is a TMR based formalism and incorporation of inverse square law factor. And this is the percentage depth dose formalism. And a change in SSD will be incorporated by the manufacturer. So their relationship, if the calculation point is not a standard SSD, then inverse square factor is needed to be accounted. PDD already contains inverse square law factor, so the inverse is simply a correction for output at Tmax when we go from a standard SSD to non-standard SSD. That is extended SSD. So various form of relation between dose and monetary unit. So this is, if you talk about the dose, this formula will be used. If you talk about the dose rate, then mu will come this ratio. It will become this ratio dose rate, and the formula is same. Whereas if you want to calculate monetary unit, then whole factor will come denominator on the other side, and then in this way you can calculate the monetary unit. So breakdown of full MUs into simple pieces. And these are the cases, and we will discuss this separately. So the case one, the depth is same. So the only the changes can be incorporated by incorporating inverse square law factor, change in SAD, so incorporated with the output factor, and it will get the dose rate. And here is the example: is SAD 1 CGY per mu at the Dmax SAD setup If you change the setup, the 100 cm SSD on the surface and the Gmax, so the SAD will be 101.5. So this factor will be incorporated, multiplied by the 1, and you will get 0.97 SPY per mu. So that shows the depth increase and the dose output is decreased. So the TBI patient usually treated an extended SSD with 40 by 40 field size. So this is the standard calibration setup. And if you go to the depth, so just inverse parallel factor incorporated, and you'll get the dose output factor. And the field size, again, it was neglected in this question. A patient is given 120 μs for each AP field with intended of SSD of 100 cm for a 10 cm tumor depth. So it's SSD setup, APPA field. This is a clinical situation. The mistake was done during the treatment on one of the fraction. Patient was treated with 1 or 2 cm SSD. So what mu are needed to be delivered for AP beam in the final fraction to make up for the total dose? So these are the clinical situation one could face, and physicists being able to should able to calculate these errors, evaluate these errors, and produce and provide solution to the clinician. Case 2, constant SAD. So for the constant SAD, only the TMR factor will be used to calculate the dose rate. So this is an example. So the dose at Dmax, the dose at any depth. So of course, the variation will be reflect on the TMR value. This is another example. For 100 μs, deliver a 6 by 6 field to the point at isocentrate cm depth. Find the dose delivered. So the field size factors incorporated. The dose will be this because it was given. If it is not given, then you can directly incorporate the TMR. There is no need to solve for the SC and SB. But if the question gives you the values of SC and SB, then of course you have to incorporate into the dose output factor. This is another question, a detailed question. Here, the important part is to understand the given data and the corresponding table, how to use those tables according to the given information. And the rest, the procedure is same. In the previous problem, the physician added a small corner block into the PA field. So with the tray factor was incorporated into those output factor. Only this has to be incorporated. Another case is constant SSD. So the PDD has to be incorporated. So the output factor is multiplied with the PDD value of set at certain depth. The output factor will be changed. In this case, the similar example, but wedge factor is also incorporated in the dose output factor. And then later, the time was calculated because this question related to COBOL 60 machine. So case 4, beam is same, the depth is changed. So TMR is the use. The ratio of TMR account for attenuation difference, and the inverse law account for the difference in the distance. So the question is, what is the best approximation for the dose at 3 cm depth from the AP beam with the dose at isocenter from this beam is 90 centigrade. So the 90 centigrade was at certain depth, that is 12.5. What will be the dose at 3 cm depth? So the first thing will come to your mind that it should be higher or the lower. Once you are clarified, once you know the answer, then of course you will be able to do the correct calculation. But if this concept was not clear, then of course you will be in big trouble then. You must try to clear your concept. So the answer is B. The TMR ratio accounts for the change in attenuation and the scatter from 12.5 cm to 3 cm depth. The inverse Floyd law factor accounts for the decrease in distance from the source. Case 5 with the PDD setup. Previous one, the SAD setup, and this one is the PDD setup. Here you can see the difference. The inverse square law factor was not incorporated because it was embedded in the PDD formalism. So this is an example of case. Patient is treated with 6 MV to sarcoma of the leg, requiring extended SSD. So here you need a minor factor to incorporate for the PDD value at certain depth. Which one of the following changes would have the greatest effect on the MU calculation for 6 MV photon beam to deliver in a similar dose? The initial calculation for 6 was 600 cm SSD at 10 cm depth. So these are the options, and the correct answer is the C, changing from 100 SAD to SSD. And these are the some explanation of each point. Changing the collimator setting from 6 to 8. So increase by less than 1% due to this change in head scatter and patient scatter. So answer may be correct, but it was not that significant. Changing from 10 cm to 11 cm, decreased by 3% change in the dose for 1 cm change in the depth. Where the C, the changing from 100 SAD to 100 SSD, inverse square law. So 0.81, so those decreased by 20%. So you can see the significant change occurred due to the inverse square law factor. And those are the insignificant as compared to this value. The latter one, the adding a 1 cm plastic block tray is only decrease the dose by 4%, and adding by 1 cm bolus to about 3% per cm. So these kind of question may occur come in IMPCB examination. What has to be prepared for that? A LINAC is calibrated to deliver 1 CGY per mu for 10 by 10 field size at Addison's. 10 cm deep in a water phantom, the machine delivers 400 mu per minute. So the dose rate to isocenter will be greater than 1 CGY per mu for a tumor treated isocentrically. At 10 cm depth. The beam on time will be less than 30 seconds to deliver 200 CGY through to field size at 95 cm SSD for a point at 10 cm depth. The dose rate will exceed 1 CGY per mu for 20 by 20 field size to a point 90 cm SSD and 10 cm depth. The dose rate will exceed 4 centigrade per mu for a point treated at 190 cm SSD with 10. So again, we read the question and then we'll go to the answer. A LINAC is calibrated to deliver 1 CGY per mu. So once you read this question, you try to make the diagram on a rough page or in on your mind that what it reflects, what setup it reflects, and try to make the setup on the diagram. Then try to solve these answers. So now read. So the dose rate to the isocenter will be greater than 1 CGY per mu for a tumor treated isotonically. The beam is transversing to 2 cm less thickness. Okay. The beam on time will be less than 30 seconds to deliver the 200 CGY through them. It takes 30 seconds for 10 by 10 field size at 100 cm SSD at 10 cm depth, which is 90 cm SSD. It will take longer for 95 cm SSD due to the inverse square law factor. The dose rate will exceed 1 CGY per mu for 20 by 10. This is the same as reference setup, except the output will be few percent larger due to the collimator and the phantom scatter. The dose rate will exceed 4 CGY. The inverse square law actually 100 over 200 square, which will make the dose rate about 0.25 CDY per mu. So these are, this is a comprehensive question, and these are the data come on the RefX and the ABR paper and IMPCB paper or CMD paper. So one should able to understand this table and then try to answer these questions, which I'm not going to read right now. The question and the solutions were given, and you can try to solve yourself. So the summary of this presentation, following should decrease the dose rate. So remember these points. So increase in the distance, increase in the depth, decrease in the field size, or adding attenuator, where decrease the dose rate. Decrease in dose, more mu's are needed to give in the same dose. For the same mu's, less dose should be delivered. TMR have no inverse square law component, and the PDD have an inverse square law. These are the references of this presentation. Thank you very much, and you can put your question on the comment box. I'll be happy to answer those questions.